Hello everyone, let us continue our discussion. We are in 9th week and this is our second lecture. So in this week we are going through the design of water tank and particularly underground water tank. So let us continue with the design, and if you recall, in the previous lecture we designed the wall of a water tank. On either side the provision of water was there, and accordingly we decided the worst possible bending moment and we designed accordingly, right? So now today let us design another water tank which is underground, and the dimensions, as you can see, 6.5 meter by 4 meter by 4 meter. Now surrounding this water tank there is a soil here, and the condition is given that it always remains dry, and the tank has a roof slab. The weight of soil is given 18 kilonewton per meter square, and the angle of repose this time it is 30 degree. So we'll use M30 concrete and Fe415 grade steel. Now, if anything is not stated, then we assume that the soil surrounding the tank will not be removed at any stage. And if that is the condition, the critical loading will be either of these two. So when the tank is full or tank is empty. Now we'll consider both of them and we'll see how we are going to design. And for the design, as you can see, the wall is actually connected here at the base, and at the top it has a support, so the wall behaves as a propped cantilever, right? So we'll design accordingly. So let us see. So case 1 is what we have already discussed, when the tank is full. So now we have the maximum soil pressure. For this case, recall the angle of repose is 30 degree. So the soil pressure is 24,000 Newton per meter square. Then we find out maximum water pressure, and the height is 4 meter. So the maximum water pressure is 39240 Newton per meter square. So the net pressure will be the difference of these two. So the net pressure, as you can see here, 15240 Newton per meter square. Now due to this pressure, we'll have the maximum bending moment. Recall this we earlier discussed. The maximum bending moment at the base is pH square by 15, while the maximum bending moment over the stem is pH square by 33.5. So the maximum bending moment that produces tension away from the water phase is pH square by 33.5, and the value is here 7278.8 Newton meter. On the other hand, maximum bending moment producing tension near the water phase, which is here, is 16,256 Newton meter. Now let us consider the second case when the tank is empty. In that case, the soil pressure will act, which is 24,000 Newton per meter square, and for that soil pressure, the bending moment again producing tension near the water phase is pH square by 33.5, and in this time you will have 11,462.69 Newton meter, right? On the other hand, bending moment at the bottom producing tension away from the water phase is pH square by 15, and which is 25,600 Newton meter. Now for our design, we adopt, recall, M30 concrete and Fe415 grade of steel, and we adopt this code which we discussed in the previous lecture. So as per this code, sigma C is 10 Newton per millimeter square and sigma T is 130 Newton per millimeter square, and the modular ratio is 13. So we can find out the value of K, which is 0.67, and R or Q is 3.323. Now let us start a design. So we have two different cases and two different locations. So altogether we have 4 different bending moments, as you can see in this table, to consider, and then based on that we will actually design the complete section and we will find out the steel requirement. Now for that, again, the actual tensile stress in the concrete due to bending has a maximum permissible limit of 2 Newton per millimeter square. Again, you refer to table 1 of this code. And to satisfy these conditions, we have to first find out the capacity of the section, which in this case is 0.333 BD square. So it is effectively sigma times Z, which is for the rectangular section BD square by 6. So that's how we get this 0.333 BD square, and we equate that for the applied maximum bending moment out of all these 4 options, which is 25,600. So if you equate this for a B is equal to 1 meter, then we get the total depth D is 277.2 millimeter. So what we do, we provide 280 millimeter thickness. Then if the effective cover is 40 millimeter, so effective depth small d is 240 millimeter. Now using this for the demand of 25,600 Newton meter, we can find out the steel, and that is here. So the steel requirement is 1225 millimeter square. So we can provide 16 millimeter diameter bar, and you can also find out the spacing. Let us provide a spacing of 160 millimeter center to center. So you can see the steel here along with its spacing, right? Okay. So now let us find out the steel required for the other face. You can see we have considered the bending moment, maximum bending moment, producing tension away from the water face, which is here. Then maximum bending moment producing tension on the water face, which is 16,256. And for that, again, we find out the steel requirement, and that is 778 millimeter square. So we provide 16 diameter bar at the rate of 150 center to center. That means we provide 804 millimeter square, and that you can see here. So now both the faces have the required amount of steel based on the maximum bending moment that we have evaluated. Then for checking stress against cracking, so let us first find out the position of the neutral axis. For that, again, we have to take the moment about neutral axis, and if you recall, this was the expression we discussed at the very beginning of this course. And in this expression, we know everything, so we can find out N, so which is 141.8 millimeter. So the moment of resistance from the tension zone, we can consider using this expression, where 0.82D is the lever arm, and you can see the evaluation here. Then cracking stress due to the first bending moment of 25,600 Newton meter. For that, what we do, we first find out the maximum tensile stress CT, and for that we use this expression. If you recall, earlier also we derived this expression where we use the modular ratio to convert the steel area into equivalent concrete area, and from there we get this expression T is equal to 79,809.6 CT. So what we do, we equate this moment of resistance with the applied moment, 25,600 Newton meter. And then what we get, CT is 1.63 Newton per millimeter square, which is less than the permissible value of 2 Newton per millimeter square. So it is okay. Then we repeat the same exercise for the other phase where we have the bending moment of 16,256 Newton meter. And then again we repeat the same exercise. We find out T equal to 77,826.4 CT. And then that we equate with the applied bending moment here. So in this phase, we have CT is equal to 1.06 Newton per millimeter square, which is again less than 2 Newton per millimeter square. So the design is okay. Now recall we have to also provide the distribution steel. In this case, again we use 8 millimeter diameter bars at the rate of 160 center to center. I leave this as an exercise for you. You can use the previous expression that we did for distribution steel, if you recall, 0.3%, and then based on that we evaluate the spacing for distribution steel. Then we go to the design of the roof slab. For the roof slab, again we have to consider the depth of the slab, which is 170 millimeter, and for that we have a dead load or 4,250 Newton per meter square. Then we design it against the live load of 1,600 Newton per millimeter square. So the total load is the summation of these two. And using this as the uniformly distributed over the slab, we can find out the maximum bending moment, which is here, 13,395.33 Newton meter. Now, for this bending moment, we use our regular expression. Recall this is R or Q BD square, which is equal to the applied moment. So we can find out the depth required, which is in this case 63.5 millimeter. So again we provide 40 millimeter or 4 centimeter of cover. So the effective depth is actually 70 millimeter. Now based on that we can find out the steel requirement. The steel requirement is 2197 millimeter square. So we can provide 20 millimeter diameter bars at the rate of 140 center to center. Just check the spacing whether it is sufficient or not. That exercise I leave it for you. So again we have to go for the distribution steel. We provide 10 millimeter diameter bar with a spacing of 230 millimeter center to center. The last component we have to design is the base slab. For the base slab, again recall we have two different load cases. Case 1 is when the tank is full. When the tank is full, we have the full water pressure acting over the base. So we consider 1 meter run of the tank. So weight of the roof slab we get here, it is 12,540 Newton per meter. Then the same from the walls, which is 56,000 Newton per meter. So the total weight is 68,540 Newton per meter. Now you should note that the water pressure on the base slab and the weight of the base slab will directly counteract by the ground pressure, and therefore are not included in the bending moment calculation. So the net upward reaction we get is 13,708 Newton per millimeter square. Then the next task is to find out the bending moment. You can see the loading diagram here. So we have supports at these 2 points. We already have designed the thickness of the wall. So from that we can find out from this location to the distance of the extreme fiber that you can see it is 0.86 meter. So the bending moment at the center due to the loading that you have already considered here is 11,651.8 Newton meter, and it will produce tension on the water side. Now let us consider water pressure and soil pressure acting on the wall that will produce a moment of this that we have already evaluated. So the total bending moment at the center will be the summation of these two. So it is 27,907.8 Newton meter. Then at the end, we have to find out the bending moment which is hogging due to this loading here. That hogging bending moment is obviously 16,256 Newton meter, and the sagging bending moment we can find out. We know the reactions in Newton per meter. So sagging bending moment is 5,069.22 Newton meter. So the net bending moment is the difference between these two, which is 11,186.78 Newton meter. And it is producing tension again on the water side. Then we have the case 2, and for that the tank is empty, and for this condition again the bending moment at the center due to vertical loads that we have already figured out, it is producing tension on the water side. Then bending moment due to soil pressure, which is 25,600 Newton meter, producing tension away from the water side. So the net bending moment at the center is 13,948.2 Newton meter, which is again producing tension away from the water side. Then bending moment at the end is the summation of these two, which is 30,669.22 Newton meter, producing tension away from the water side. So we prepare this table as we did in the previous case. So we have two different load cases and the bending moment at the section and midspan. So we have the values of the bending moment as you can see on your screen, and the tension side also identified. So first start with the thickness of the base slab, which is say capital D millimeter. Now from the cracking stress considerations, so we have to equate this RBD square with the applied moment. So you can see R is 3.323, B is 1000. So we have RBD square, which is equated to this value of the bending moment at the midspan corresponding to load case 1, and we have D is 91.6 millimeter. We have already provided a depth of 300 as base. So if we consider a bigger effective cover at the base, so effective depth is 240 millimeter. Just note this value, I will come to that in a minute. At the base we have a thicker section. So the steel requirement AS is 1315 millimeter square. So we try with 20 millimeter diameter bars and the spacing is 235.3 millimeters. So we can provide 25 bars at the rate of 230 millimeters center to center. Then if you go back, we have the other load case producing a moment of 30,669.22. So for that, again, let us find out the steel, which is 1467 millimeter square. So we provide 20 millimeter diameter bar at a spacing of 240 millimeter. So let us provide 25 bars at the rate of 200 center to center. That satisfies the requirement of steel. So we provide 1570 millimeter square as opposed to 1467 millimeter square that is required. Then again we check the cracking stress. For that we have to first find out the neutral axis. This expression is familiar to us. So we first find out the location of the neutral axis, which is N, that is 150.7 millimeter. So first we consider the bending moment of 27,907.8, that is the load case here. And for that, the cracking stress, that is CT, is by equating this with the applied moment. So we get CT is equal to 1.66 Newton per millimeter square, which is the less than the permissible value of 2 Newton per millimeter square. So the design is okay. Then we consider the other load case, that is producing a bending moment of 30,669.22 Newton millimeter, and for that again we repeat the same exercise. We get CT, that is the tensile stress is 1.81 Newton per millimeter square. So which is less than again 2 Newton per millimeter square, that is the permissible value. So the design is okay. Then we provide the distribution still. For this case, we have 12 phi diameter bar, and spacing we can find out. The requirement of steel is 900 millimeter square. So the spacing is 120 center to center. Here comes the detailing. As you can see, we have the plan view. So you can see the steels in the walls. So here is the longer side, here is the shorter side, and we have the main bars. These are the main bars. On the either face, outer face, we have 16 phi bars at the rate 160 millimeter center to center. Inner face, we have 16 phi bar at the rate 250 center to center. Then we have distribution steel 8 millimeter at the rate 160 center to center. So that completes the design. So in the plan we have studied. So now this is the cross section. We have the walls, side walls here with the details of reinforcement. We have the roof slab where we have 10 phi bar at the rate 230 center to center. And on the other direction, we have 25 bar at the rate 140 center to center. Similarly, for the base slab, we have the steels on one direction 25 at the rate 200 center to center. The other direction, we have 25 at the rate 230 center to center. Right? Then along the longer side, we have 12 phi at the rate 120 center to center. Now this main bar again comes here and it stops there. Recall, we have to consider the development length before we stop this. These are familiar to us, so that check is not shown here, but all of you can check that very easily, and accordingly you have to provide sufficient length here. Right? That is an extra check you have to do, but again we don't repeat that. You can easily complete that exercise. So with that, let us conclude our discussion on underground design of tanks. So you go through this design steps. If you have any query, do let us know. We will clear your doubt. Thank you very much.